In this video, I want to do a little bit extra. Let's start with this. That should have upset you. We know perfectly well that if we have a real number, we could not solve that equation. What happens if we take z as a complex number? So let's put z equal to x plus iy. X and y are both real. This will give us that e to the x plus iy is equal to minus 2. Well, e to the x plus iy is e to the x e to the iy. If we now use Euler's relation, we get e to the x cos y plus I e to the x sine y. Has to be minus 2. Well, if we equate imaginary parts, on the left-hand side, we've got e to the x sine y, and on the right-hand side, 0. Well, this tells us that sine y must be 0, since e to the x cannot be 0. X is a real number. Therefore, y is equal to n pi. Let's look at real parts. On the left-hand side, we've got e to the x cos y, and on the other side, we've got minus 2. This tells us that cos y has to be less than 0, has to be negative. E to the x is greater than 0 if x is a real number. Putting these two ideas together, that y equals n pi and cos y is less than 0, tells us that y has to be 3 pi, pi, 5 pi, can't be any of the even pi's. So y has to be 2n plus 1 pi. And that tells us that cos y must be minus 1. If that's the case, then e to the x cos y is minus 2. E to the x has to be 2, in which case x has to be natural log of 2. So we now have that z is x, which is log 2, plus iy is 2n plus 1 pi times I, where n can be any integer. So we can solve e to the z is minus 2 if we use complex numbers. I now want to look at the connections between cos and cosh and sine and shine. These are called the linking equations. We know from Euler's relation that e to the ix is cos x plus I sine x, and e to the minus ix is cos x minus I sine x, and we should be fairly familiar with adding these and dividing by 2. We get a half e to the ix plus e to the minus ix. Well, that is just, if we allow complex numbers, the definition of cosh ix. So cos x is equal to cosh ix. If we replace x by ix, then we get cos replacing x by ix is equal to cosh. I times ix is I squared x is minus x, and we know that cosh minus x is the same as cosh x. So we know that cosh x is cos ix, and that cos x is cosh ix. So there's my connection between cos and cosh. If I go back to the first equations, and instead of adding, let's subtract and divide by 2i. We get that sine x, subtracting, we get 2i sine x So if we divide by 2i, we get sine x. If we now look at our definition of sine, this is 1 over I times sine ix. So there is a connection between sine x and sine. Play the same trick again. Replace x by ix, and we get sine of ix is 1 over I sine ix times I is minus x, which is minus 1 over I sine x, because sine of minus x is minus sine of x, and that gives us I sine x. And so sine x is 1 over I sine ix. This now gives us our linking equations, which are going to be that cos x, looking up the page, is cosh ix, and cosh x is cos ix. And we also have that sine x is 1 over I sine ix, and that sine x is 1 over I sine ix. So there is a connection between cos and cosh and sine and sine. Now we have another unpleasant looking equation. Sine z equals 2. You have always been told that sine can never be bigger than 1. Well, what happens if we start looking at complex numbers? Let's put z equal to x plus iy, where x and y are of course real. This gives me sine of x plus iy is equal to 2. Addition formula, sine x cos iy plus cos x sine iy is equal to 2. Well, let's use the linking equations. And we get that cos of iy must be cosh y. So we have sine x cosh y, and over here we want sine iy. Sine iy is I sine y plus I cos x sine y equals 2. All right, let's solve that then. Imaginary parts, left-hand side, cos x sine y is equal to 2. Sorry, imaginary parts, cos x sine y is equal to 0. This tells us that cos x equals 0 or sine y equals 0. If sine y is 0, then y equals 0. And if y equals 0, if we look at the real parts, you get sine x cosh 0 is 2. That tells us that sine x would have to be 2, because cosh 0 is 1. X is a real number. That is not possible. So we can't have sine y is naught. We've got to rely on cos x is naught. Cos x is naught means we must be on the pi by 2's. And so x must be 2n plus 1 pi by 2. That will do all of the pi by 2's for n any integer. Let's move up a bit more space. So we got that from the imaginary parts. If we look at the real parts now in more detail, real parts, you get sine x cos y is equal to 2. X equals 2n plus 1 pi by 2. Sine pi by 2 is plus 1, sine 3 pi by 2 is minus 1, etc. And therefore sine x is plus or minus 1. But cos y is greater than naught. That's actually greater than or equal to 1. And therefore sine x has to be plus 1. If sine x is plus 1, then x has to be pi by 2, 5 pi by 2, 9 pi by 2, etc., 4n plus 1 pi by 2. In which case sine x is 1, cos y therefore has to be 2. And so y is equal to r cos 2. Logarithmic form is log 2 plus root 2 squared minus 1 is log 2 plus root 3. And so the solution of my equation is that z is equal to x, which is 4n plus 1 pi by 2 plus I times y, which is log 2 plus root 3. So not only is there a solution to sine z equals 2, there's an infinite number of solutions. N can be any integer.